Okay, to finish out chapter 8, today we will do section 8.4. Get you started with something that I found to be very, very interesting, kind of a statistical phenomenon we should be talking about this morning. The book by Dan Ariely, Irrational Predictability, he describes a study that was done at MIT. They got volunteers to come into a med center. The trainers, they were dressed up in lab coats with stethoscopes hanging around their neck. They looked like doctors. They explained to the volunteers that they were going to test their resistance to pain. They then took their heart rate, their blood pressure, et cetera, et cetera. They wired the volunteers up to a very complicated looking machine that proceeded to give them electrical shocks. The volunteers then recorded their pain on a computer on a scale from I can't feel it to unbearable. After the test was over, the staff told the volunteers they're going to have a chance to evaluate a new pain pill called Belladone. Each volunteer swallowed one of the $10 pills. Pills were rather expensive. And then they retook the electrical shock test after taking the pill. Almost every volunteer reported less pain, okay? Pain pill must be pretty good, huh? Then they brought in a second group of volunteers, came in, the tests were done exactly in the exact same way, except they were told that the pills only cost 5 cents each. This time, only about half the volunteers reported less pain. Very, very interesting. Before we go any further, I think it goes back to the bias of scrutiny that we talked about some time ago. If you remember, a faculty member, a professor, has set up a little bit of a snack bar on a college campus and put different pictures on the wall, and they always got more money turned into the snack bar when there were a pair of eyes. If you think you're watching, someone is watching you, you tend to behave differently. And what I think this study thus far, as we talk about it, the first group was told the pills were very expensive. They cost $10. And probably the volunteers taking the study kind of fell into that same situation with the bias of scrutiny. They knew they were being watched. They wanted to tell the very distinguished looking doctors, they wanted to tell the doctors what they thought the doctors wanted to hear, and that the pain pills really worked because they were expensive, they were new, they were something ingenious that was going to help pain. The second group told the doctors kind of the same thing, what they thought the doctors would want to hear, that the pain pills were cheap, they probably did not work very well. There's also one other side to this. What is even more interesting was that the Belladone, quote unquote, was really just a very large vitamin C pill. It really didn't have anything to do with pain at all, which is rather an interesting thing. So the expectation bias, or the bias of scrutiny, where you tell the people administering the survey what you think they want to hear. The other thing I think we need to talk about is the Stockholm Syndrome, where this is named for when someone is kidnapped, and which happened in Stockholm, Sweden. When someone is kidnapped, you are more than likely, after a while, to start bonding with the kidnapper, and you want to do what the person in charge of you thinks should be done. Very similar situation in this particular study, which I thought was extremely interesting. Okay, so chapter 8, section 4. We found out in chapter 7 if the variable is normal, or if n is bigger than 30, x bar is normal, and z is x bar minus mu all over population standard deviation divided by the square root of n. Old news, we know this, but what if we don't know the population standard deviation? In fact, in a lot, or maybe should I say the majority of statistical studies that are done, that you don't know the population standard deviation. Well, the only option you have is to use the sample standard deviation, okay? You can look on page 343 in your text to see the graph of what's going to happen when you use the sample standard deviation 343 instead of a population standard deviation. There are two graphs down toward the bottom of that page. One is histogram using z-values. One is not using, it's using the sample standard deviation using something called a t-score, okay? Both graphs appear to be very, very closely normal, okay? It's slightly different, but not much. So when you cannot use z-scores, which we know are called standardized scores, when you can't use z-scores, you have to use what are called t-scores, and we will have to use the sample standard deviation instead of the sigma, the population standard deviation. So that's all about what we're going to be doing today, okay? Z-scores are standardized, t-scores are called studentized, okay? Now you're going to see this in the homework. I guarantee you will never see it from me on a test, but you will see this phrase in the homework. Studentized just simply means we're using the sample standard deviation and t-scores, whereas standardized, we're using z-scores and the population standard deviation, okay? How exactly does it work? Well, let's just a couple other things, and then we'll actually do some problems. As n gets larger, a t distribution gets more and more normal, quote unquote. In other words, as n gets very, very big, t-scores are very, very close to z-scores. You could use either one. As t-curve is symmetric about x equals 0, just as a normal curve is. The area under a t-curve is 1, just as a normal curve with z-scores. T sub alpha is also the t-value with an area to the right, just like z sub alpha has an area to the right of the z-score of alpha. Area to the right of a t-score, the area is alpha to the right. But also the symmetry. So if the area to the right of a positive z-score is the same as the area to the left of a negative z-score, right? Same thing happens with t's, okay? All right, to find t sub alpha, there's another difference. The chart is different, okay? So let's talk about the chart. On the chart, if you have the chart that I gave you, it should be on the flip side. You can also find it on the inside back cover of your textbook. You can also find it in the appendices. I think it's page 8 or 9, something like that. So there's a lot of different places you can find a t-chart. Now, suppose I wanted to find t sub 0.05, okay, on a t-chart, okay? What I'm trying to find is a t-value that has an area of 0.05 to the right of that particular t-value, okay? On your t-chart, you'll see right away the t-chart looks very, very different from the z-chart. Why did they do it that way? That is a good question. I can't answer that. Go at the top to all the columns, and you want to find t sub 0.05. So find that in the top of your column, t sub 0.05. And now, to study of 15 people, you would think you're going to go down to 15, okay? But that's not the case. You're going to go down to 1 less, you're going to go down to 14, and you should be looking at 1.761. Now, to help you remember this, okay, when we do the standard deviation of a population, everybody remember how we did that way long time ago? You had a column of x values, you had x bar, you subtracted when we were finding standard deviations, you squared the difference, you added them all up, and you divided by 1 less if it was a sample standard deviation. If it's a population standard deviation, you divide by the total number taking the survey, okay? So in t-scores, it's exactly the same thing. When you go to look up 15 people on the chart, you go to one less. The column has a DF, which stands for degrees of freedom. We're not going to even bother discussing what that is or what that means. It's beyond the scope of this course. But you go down to 14, you go to one less when you're using a sample standard deviation and a t-score. Okay? Okay, so how about some problems? Let's talk about some problems here. Find a confidence interval, and we're going to do the same thing. We want to do a 95% confidence interval, so let's do it. So we're going to draw a bell-shaped curve. X bar is 25. We have n equals 36. S, sample standard deviation, is 3. And we want a 95% confidence level. So this is 0.95. Alpha is 0.05, which means the area to the right and to the left is 0.025. Okay? All right. So what we know that the margin of error is equal to the z value, but in this case, because we're using sample standard deviation, we've got to do the t value times the sample standard deviation all over the square root of n. Okay? One more comment on this subtracting one business. When you're finding a sample standard deviation, you subtract 1 before you divide and take the square root. When you're looking up a t value, you subtract 1. You subtract 1 on your degrees of freedom column to get your t value. But you do not subtract 1 when you're taking the square root here. Square root of n is simply the square root of 36. All right, so let's do it. Okay, so I have 0.025. I know because it's a value for the sample, I have to use a t-score. I'm going to go to t sub 0.025 on the chart. I'm going to run my finger down that column until I get to 35. And at 35, it should be 2.03. So I have 2.03 times 3 divided by square root 36. Do the math. I can almost do this one in my head. Square root of 36 is 6. Divided into 3 is a half. A half of 2.03 is the margin of error. Should be 1.015. Okay? All right. So next, what I want to do is, let me double check the math here. I did it all in my head, but I want to do it again. So I've got 1.015 or 1.02 if you round off. Okay. So what's the confidence interval? I'm 95% confident that the actual population mean is 1.015 added and subtracted 25, or if I round off to make it easier, 1.02. If you subtract off of 25, you're at 23.98. If you add the 25 to 26.02. And there is your confidence interval. Okay? 95% confident the actual population mean is in that range. Or another way, if I use 25 for the population mean, I can be 95% confident that the biggest error I will make is 1.02. Got it? Next one, X bar is 35. N equals 36. Doggone it. N is equal to 20. N is equal to 25. Okay. S equals 4. And we want to do 90%. All right, so this is 0.90. Alpha is 0.10, which means area at each end is 0.05. So to find my margin of error, I'm going to look up a t-value. I want a t-value with an area of 0.05 to the right. So I go to t sub 0.05 and I go down to 24, which is 1.711 times standard deviation, 4 all over square root 25. Okay? Do the math. 4 divided by 5 is 0.8, so 1.711 times 0.8 is 1.37. I'm going to add and subtract it. I would get 36.37. Subtracting it off, can I do that in my head? 34.63. Okay? And looks good. 33.63. Sorry, darn it. Yes. Okay? I am 90% confident the actual population mean would be in that range, or if I use 35 as an approximate population mean, I can be 90% confident that the biggest error I'm going to make is 1.37. Now, if I could just learn to add and subtract, I'd be in great shape. Let's do another one. Okay, X bar is 55. So, bell-shaped curve, 55, n equals 16, S equals 5. We want a 99% confident, 0.99, alpha 0.01. So I know that my area on the wings is 0.005. Okay? Look up a t value. So I want t sub 0.005, last column on your chart. And you want to go down to 15. We're assuming normality here. Going down to 15 is 2.947 times 5 divided by square root of 16. Okay? 5 divided by 4 is 1.25. So I can take 2.947 times 1.25, and I get 3.69. 3.69 is my margin of error. And so now I can, actually it's 3.68. Boy, I tell you, so many mistakes. 3.68. So if I add it to 55, I'm at 58.68. If I subtract it from 55, I'm going to be at 51.32. I think. Do I trust myself that that's right? Yeah, 51.32. Okay? So that takes care of confidence intervals. Let's go on and do one that's a little more strange looking. Find a 95% confidence interval, X bar. Got some strange numbers in it. Is 513.32. N is 25. S, what a standard deviation sample. Wow, 262. Because n is 25, we're assuming it's going to be close to being normal, where you can do a probability plot. All right, the big thing is, if S is not given, now we have S, but if it's not given, you're going to have to find out. Can you do it on your calculator or make a chart? I don't care how you guys do your sample standard deviations on these problems, but you know for a fact that come test time on this, which is going to be coming up in a couple days, come test time, you know I'm going to give you a problem without the sample standard deviation, and you're going to have to work it out, okay? So if you have trouble doing it on your calculator, do it by the chart, or get in touch with me, and I'll walk you through doing it on your calculator. All right, so let's do it. We want a 95% confident interval. This is 0.95. Alpha is 0.05. This is 0.025. So we're going to have to, for our t value, go to t sub 0.025 and go down to 24. T sub 0.025 down to 24 is 2.064, 262 over square root 25. Okay, do the math. And I get 262 divided by 5, which is the square root of 25, times 2.064, and I get 108.15 for the margin of error. Don't trust myself. Hey, I did it right, 108.15. So I add it to 513.32. And I get 621.47. I subtract it. And I get 405.17. And there's your confidence interval for that. Procedure's the same. You just have to remember to use a t-value when you do not know the population standard deviation. Now, the next problem deals with a problem in the book that I just thought looked kind of interesting. So let's take a look at that. It's on page 347. And on page 347, we want to do a 90% confidence interval for chicken consumers only. Okay, so we want a 90%. This is 0.90. Alpha is 0.10. Area on the wings is 0.05. Okay? You will notice that I have figured out the X bar and the sample standard deviation. And once again, okay, I hate to keep repeating myself. If you don't have a standard deviation, and if you have to calculate it, it's a sample standard deviation and you have to use a t-value. All right, so X bar is 67 point, let's call it 13. S is 11.11. And if you look in the chart, there are 17 randomly selected people. We're assuming normality. And one of those people does not eat chicken. So we're going to have to knock it down to 16. So N is 16. Okay, t-value. T-value in this problem, we're going to go to T sub 0.05, and you're going to go down to 15, which is 1.753 times 11.11 all over square root of 16. So it's 11.11 divided by 4. So we can do that. Get the answer, take it times 1.753, and I get a margin of error of 4.87. Okay? 4.87. Perfect. All right. So now I add and subtract it to the mean, which is 67.13. We said we were going to round it off. So 67.13 plus 4.87 comes out to 72. And 67.13 minus 4.87 comes out to 62.26. Once again, how about an interpretation? Can you write or tell me an interpretation on your homework? And also, you're going to have to do it on the test. If I use 67.13 pounds for the population mean, how much chicken is consumed, okay? I can be 90% confident that my largest error would be 4.87 pounds. That's one way to make an interpretation. The other interpretation would be, I am 90% confident that the actual population mean is in that range, okay? Oh, what is this? Air traffic control. I'm going 400 miles an hour and I need to land this thing on a floating narrow runway, so I'd prefer something better than 95% confidence in those coordinates. An aircraft carrier, a pilot, a statistical cartoon. What could be better? Homework. Homework. Remember, your population is not normal. You can't do it. Okay? Your problems will all tend to be normal. All right? Here's book problems. And one extra problem. Notice in this extra problem, you do not have a sample standard deviation. You don't have a population standard deviation. You're going to have to find the standard deviation and do a t-test. Okay?